So before we start the discussion of stiffness method, we have to see that both these methods, the flexibility method and the stiffness method, they are fundamentally developed to solve indeterminate systems. Now, flexibility method cannot be used to solve a determinate system, obviously, because it uses the ability to solve a determinate system as as the very basis of flexibility method. Because in the flexibility method, whatever system you have, if it is indeterminate, you resolve it to make it determinate. Okay. If the system is already determinate, you solve it directly. Okay. So the flexibility method as such cannot be used for solving determinate methods because it is already determinate. That is the first part of the flexibility method. Okay. So that is kind of a trivial answer. In stiffness method, it can be used for solving determinate as well as indeterminate problems, and the procedure is exactly the same for the two issues, for the two types of problems. Okay. In the flexibility method, we have a, let's say, we have an indeterminate system, and we want to use the flexibility method. The approach is that we release some of the restraints, that is some of the displacement constraints. Okay, so the constraints are on the displacement. So you may have a boundary condition that you may release, you may have two member joining here that we may disconnect. These are all displacement constraints. So we release some of the displacement constraints, meaning that we make the forces at those locations zero. Correct. So we artificially make the forces at some locations zero, and in the process we make the system determinate. Okay, so if I can draw a line number, okay, and we will plot the degree of indeterminacy, degree of static indeterminacy. Okay, so we are plotting the degree of static indeterminacy on this system. So if our system is somewhere here, let's say it has this degree of static indeterminacy 3. Okay, so the flexibility method, what it says is that, okay, you have got your system which is lying somewhere here on this line. What you need to do is, this is the 0 point. Beyond this, behind this, what do you have behind this line? Behind this point, what do we have?
We have instability.
Unstability.
Unstable system. Yes. This unstable system, you don't want to go there, of course. So the flexibility method says, you make your system, if this is the system that is given to you, you make it jump here. Okay. And in the process, you released 3 forces, that you made 3 forces 0. Okay. Forces also mean moments here. So then you need to solve 3 equations. These are compatibility equations. Okay. So you need to solve these 3 equations to get the system, to solve this system. So first you release these 3, make it determinate. Okay, determinate is a more flexible, more simpler system. Okay, so you make it determinate by releasing these 3, and then you work your way back by solving these 3 equations. Correct? That's the method. That is the flexibility method, and that's how you get the solution for this system. The stiffness method, what it says is that, the stiffness method says that let's consider some locations as degrees of kinematic indeterminacy. DOF, degrees of freedom, or kinematic indeterminacy, and we will have some discussion on what is kinematic indeterminacy or degree of freedom. Okay, all the DOFs or kinematic degrees of kinematic indeterminacies, sorry, when I'm talking I cannot spell things. Kinematic indeterminacies are restrained. So in this particular case, in case of a flexibility method, we were releasing the forces. That means we were making the forces as 0. Here what we are doing is we are making all the displacements at every kinematic indeterminacy as 0. Okay, and in the process we are making that system an extremely indeterminate system. We are increasing the degree of static indeterminacy very severely. Okay, so its static indeterminacy is increased, and then once you solve that system, and we will see how to solve that system. Once you solve that system, then basically we start releasing one point at a time. So we start releasing the displacements that we had restrained. Okay, we start, so the displacement that were set to 0, we start releasing them one at a time. So there will be those many equations that we had additionally tied. All those have to be released back, and then these are the equilibrium equations here. Equations have to be solved. So those many equilibrium equations have to be solved to bring it back to where we were originally. Okay, so as you can see, one is exactly opposite of the other. In one case, we reduce the degrees of indeterminacy to 0. In the other case, we get it to maximum possible. Okay, and then we work our way back. In this case, we work our way up. This is stiffness method. Okay, now from here it is obvious, if we were already at the determinate level, okay, then the flexibility method won't work because you're already at the determinate system. But the stiffness method will still work. You need to jump to the maximum level of fixity that you can provide to the structure, and then release all of them one by one, so that you come back here to the determinate system. So if we were starting from a determinate system, you can still use the stiffness method. Okay, so stiffness method does not change. The way you use the stiffness method does not change at all, whether you are dealing with a determinate system or an indeterminate system. So you don't even have to figure out whether the system is determinate or indeterminate in the stiffness method. Okay, that is a major advantage for behind using a stiffness method. You don't have to make choices of which degrees of freedom to release. Okay, because essentially what you're doing, you are restraining all the degrees of freedom rather than releasing them, and then releasing the ones that are artificially restrained. So that's why computers like the stiffness method. Okay, these are the steps that you have to go through. We will learn about these steps one by one. So basically, the idea is that, let's say you divide your system into a number of members. Okay, and how you divide that system into which members, that is your choice. So let's say if I give you one system which looks like this. You guys are following me, right? I'm not checking with you after every step whether you are able to follow the discussion or not. If you have any doubts, please feel free to ask. So I have this frame. Let's say this is an indeterminate frame, right? And I want to solve this system. This length is L. This length is L. This is a plane frame. Let me write it. It's a plane frame problem. Okay. Can somebody tell me degree of static indeterminacy? How much? 1, sir. Anybody else? This joint is a rigid joint. This is a rigid joint. Yeah. Every it is 1. Correct. This is the only vertical degree of freedom. If you release it, then it becomes a cantilever, which is a statically determinate system. Fine. This is free. This rotation is free. So only one is extra. Extra restraint is only one. Fine. Static indeterminacy is straightforward. Kinematic indeterminacy. How many?
5.
At the bottom support, how many?
0, sir.
0.
0.
0.
How many here?
3.
3. Okay. How many here?
2.
Okay. So you got 5. Does that look good to everybody? Everybody agrees, right?
Yes.
What?
Yes, sir.
And who gave the answer of 5 first? Who was it?
It was me, sir.
Dipsy. Okay, Dipsy. Fine. So, Dipsy, what motivated you to select this location, and this location to calculate the degrees of kinematic indeterminacy? Why did you select these 3 locations? You selected these 3 locations only, right?
Because sir, we calculate displacement at joints, right? And the supports. That's why.
Where do you define a joint? Let's say I had this beam which was thicker than the upper beam. Then what would be the kinematic indeterminacy?
5 plus 3, 8.
5 plus 3, 8, right? So you are calling a joint when there is some kind of a discontinuity appearing there.
Yes, sir.
Agree? Yeah. So at this location, for example, your member was changing its direction. So what would happen is that your vertical movement will translate as a shear movement for this one, right? So the axial movement of this frame member will translate as the shear movement or lateral movement of this member. Correct? So that is the level of indeterminacy or the level of discontinuity you are getting here. Similarly, your lateral movement of this member will translate as the axial movement of this member. Agreed? So that is also one, in a way, a discontinuity, but that may not be very convincing. Okay, so as an answer to that, why did we choose? So as soon as I change the thickness of this member or the cross-section properties of this member here in the middle, so one half of this is of a different size, the remaining half is of a different size, we immediately picked an indeterminacy, kinematic indeterminacy here, but earlier we were not picking it. Does anybody have an answer to that? Why are we doing that? That doesn't seem very fundamental, right? See, static indeterminacy was completely a property of the cross-section or property of the structure. So if I change the EI property somewhere, it did not change the static indeterminacy. It purely depended on the boundary condition and connection properties, etc. Okay. So static indeterminacy did not change, but kinematic indeterminacy changed as soon as I put a smaller or slightly bigger cross-section here. So what is really the static kinematic indeterminacy? Anybody? If I put a hinge here, if I put a hinge, of course, you will change the static indeterminacy too. But your kinematic indeterminacy calculations will also change. Okay, you want me to explain, or somebody still wants to try? I would like somebody to try.
3, sir.
It is what?
3.
3 kinematic
So it's
indeterminacy.
really depend on the flexibility of the members. If see, is a rigid beam, or like if it's the members are highly rigid, then we can take as 3. Yeah.
So that's what you're saying. So that's what Dipsy said. 3 plus 3 plus 2. Did she say 3 or did she say 2?
No, sir. Total is 3. Total
is 8, right?
So,
That's what everybody is saying. I suppose everybody is in agreement with this. So these are, to be more precise, basically there are 3 degrees of freedom, FDOFs, and there are restrained degrees of freedom. So if I say restrained degrees of freedom, then there are 3 here, there is 1 here, so 4. Free degrees of freedom in this case are 3 plus 3 plus 2, 8. So total degrees of freedom, which we can just call DOF, are 12, isn't it? Agreed, right? Everybody agrees with this? So kinematic indeterminacy is basically your free degrees of freedom in a way, right? But that still doesn't answer the question, why are we picking 3 here, and like on what basis we are selecting the degrees of kinematic indeterminacy? Actually, the idea of kinematic indeterminacy is a little bit arbitrary. Okay, you are listening to me carefully. It is entirely up to me where I define the node or the joint. Okay, but of course it also depends on the formulation where I'm going to use this value. Whatever this value is, I'm going to have to use this in some formulation, and in that formulation whether this kind of a definition works or not. So if you remember the stiffness matrix from your earlier classes, we had derived the expressions from your earlier courses, like during your BTech and earlier courses. We had derived the expression for stiffness matrix. So if it's a frame member or a beam member, it was defined as EI being constant and member being straight. Correct? For this kind of a member, you had defined the degrees of freedom 1, 2, 3, 4. And for this, you had developed the stiffness matrix or K matrix, S matrix or K matrix, whatever you want to call it. Okay? Which had terms of force required for unit displacement, and so on. That's what we had done, right? So what was the assumption there? The assumption was that EI is constant through the length of the member, right? And the member was a straight member. So as long as these two things are true, and we didn't have any hinges or anything, that is also already incorporated in EI being constant or uniform. Okay. So as long as we have these things true, we don't have to take another indeterminacy, kinematic indeterminacy or degree of freedom in that number. Okay. But if you want to, you can always. So just raising this, so that going back, you have this member. Okay. I wish EI is constant everywhere, but I can always divide this into 4 parts. So then my degree of kinematic indeterminacy would be, let's say 0 here. If I'm counting only 3 degrees of freedom, 0 here, 3 here, 3 here, 3 here, and 2 here. That is 9 plus 2, 11. I can also further divide it. It's my wish. Then another 3, another 3, another 3. You got another 9. Okay, so you got 20. It's entirely up to me how many times I want to divide. But there is no additional benefit because I already knew the formulation for this entire member length, this entire length. I already knew the formulation for that. So there was no benefit of dividing it any further. So that's how we divide this into a single part. So we take one member, one part, and we take the degrees of freedom at both ends. Similarly, this member, this part. And the reason for that is that our stiffness matrix is defined in that way. When we derive the expression for a stiffness matrix, whatever 6 EI by L square and so on, or L cube, whatever it is, 12 EI by L cube, etc. All those expressions are derived for a straight member which has uniform EI value. Okay, no hinges, nothing in between. So that's how we define the kinematic indeterminacy. Okay, everybody's on board, but still nothing stops us from defining more points of freedom or degrees of freedom along the way. Good. So for the same system, we saw that free degrees of freedom were 8 and restrained degrees of freedom are 4 for this system. And even if this was this, so not 8, 5, 2. to keep the number of equations the smallest. So kinematic indeterminacy was 5. Free degree of freedom is 5. Distant degrees of freedom are how many? 3 here and 1 here, 4. Okay. So total degrees of freedom are 9. Agreed? Okay. Any questions on this one? No questions? Okay. So in the stiffness method, what we will do is we will start with a plane beam member formulation using a plane beam member first, and then we will slowly move up. So the idea is that I'll give you an example or the derivation for a plane beam member, and once we know that, then the rest of it is so like axial behavior is very pretty straightforward. Torsional behavior, again, the way we formulate it is very straightforward. It's not really that straightforward, but we ignore the other complications of torsional behavior. So then those parts can be very easily added when we translate into a frame member. So we will start with a plane beam. Okay. So a plane beam, this is the member here. You can see it, right? At the top, this is a plane beam. So a plane beam, when I say it's a beam member, that means it cannot even deform in the axial direction. Okay. There is no axial deformation in the beam. That means we can ignore the degrees of freedom in the axial direction. So what degrees of freedom are available to us? In direction of 1, that is lateral movement at this joint, rotation at this joint, lateral movement at this joint, and rotation at this joint. Fine. These 4 degrees of freedom are available to us. In the stiffness method, so what is the meaning of stiffness?
Force per unit displacement.
Louder, please. I couldn't hear you clearly.
I mean, a force for unit displacement, sir.
Correct, exactly. So it is exactly opposite of flexibility. The flexibility value was basically displacement for a unit force. So you apply unit force, how much displacement do you get? Okay, and that could be you apply force here, how much displacement you get here. It does not have to be in the same degree of freedom. So you apply unit force here, how much displacement you get here. That could also be one flexibility term. Stiffness term is exactly opposite. What it says is you apply a unit displacement at some point, and how much force do you have to apply at various locations to achieve that displacement here. Okay. The idea here is when we calculate the stiffness terms, we make sure that when that degree of freedom is having a unit value, all other degrees of freedom are still having 0 value of displacement. Okay. So if this is my beam, and as we had pointed out, we had numbered the degrees of freedom 1, 2, 3, and 4. So if I provide or if I introduce a unit deformation in degree of freedom 1, but I make sure that there is no deformation in degree of freedom 2, that means the slope here does not change, the slope is 0. And there is no displacement at 3, there is no movement here, and there is no rotation at 4. Okay, that means the slope is 0. Only delta 1 is 1. Then there would be different forces required at the 4 locations, 1, 2, 3, 4, at the 4 directions. Okay, those forces will be called F11, F21, F31, F41. So the first appendix, what is it called? The subscript. The first letter in the subscript corresponds to the force degree of freedom, and the second one corresponds to the displacement degree of freedom. So since we are applying unit displacement in the first degree of freedom, therefore the second subscript is always 1. The first subscript corresponds to the degree of freedom in which we are talking about the force. So likewise, there will be 4 such force values, which will make sure, so if you apply these 4 forces, you will make sure that you will get unit displacement in 1. Okay, or in other words, if you want to make sure a unit displacement in 1 and no other displacement in any other degree of freedom, you have to apply these forces. Okay, it's vice versa. Either you apply these forces to get this displacement, or you apply this displacement and you will get these forces. Similarly, you can apply, you can get a unit displacement in second degree of freedom, which has this kind of a deformed shape. Okay. In this kind of a unit displacement, you would require four forces again: F12, F22, F32, F42. Again, at four locations, so therefore, the forces are acting in four locations: F1, F2, F3, F4, and the second subscript corresponds to the unit displacement in the second degree of freedom. Fine. Likewise, you can define the force coefficients that will produce unit displacement in 3 and force coefficients that will produce a unit displacement in 4. Okay, and these unit displacements and are all in the positive direction. So vertically upward is positive. So delta 1 is positive, delta 3 is also positive, delta 2 is anti-clockwise positive, delta 4 is anti-clockwise positive. Okay, these are not internal displacements, these are actual displacements. All right. So the question comes, how do we get the value of these 4 or these 16 terms? You can see that 16 terms are here, right? F11, F21, F31, F41, and likewise. There are 16 force terms that we need to calculate the values of. So what we will do is we will quickly do a formulation for the beam, for a plane beam problem, okay, or plane beam member. We will do the formulation for a stiffness method, and then we will go on to solve one simple problem which has plane beam system, and then in the process we will learn the entire method and the philosophy behind it. Instead of just me talking and you listening, let's do some problems. Okay, so let's do some derivation for plane beam problem. So there are two fundamental types of deformations we are applying here. One is delta 1, the other one is delta 2. Now you can later on, delta 3 and delta 4 are just a variation of that one, right? So you can just, you may have to be careful with the signs. So delta 2 is equal to 1 is very similar to delta 4 equals to 1. Only thing is that these forces will switch their locations. Okay, that we can do very easily. Fine. So we will derive expressions for delta 1 is equal to 1 and delta 2 is equal to 1. And we will get the values of forces, which will be the components of our stiffness matrix. Okay. Any questions so far? So first we are learning how to develop the stiffness matrix. Development. Stiffness matrix. So starting with a plane beam member. This is a plane beam member. As you know, for each member, we restrain all the degrees of freedom. So which are the degrees of freedom available to this member? As we discussed, 1, anti-clockwise, 2, 3, 4. We'll call it 1, 2, 3, and 4. Okay. These are the 4 kinematic indeterminacies or degrees of freedom available for this member. Fine. Let's say the length is L and flexural rigidity is EI. Okay. Now, what do we want to do? We want to know if we restrain this member completely at both ends, we don't let it move laterally or rotationally, but then we force it to move laterally in the 1 degree of freedom, in the direction of 1 degree of freedom. By how much? By 1. So we make it this end, we make this end move by 1 millimeter, 1 unit. Okay. And we want to know how much force will be required. That will be my F11 term. How much moment will be required? That will be my F21 term. How much moment will be required here? F41 term. And how much force will be required here? So F31 term. Okay. How do we do? How do we do this? Which method can we use here to solve for these force terms? Anybody? See, we are developing a formulation for solving indeterminate systems, or it can be further used for solving determinate systems too. But in the formulation itself, we want to develop the stiffness matrix. And for that stiffness matrix, essentially what we are required to do is this system that was a fixed beam. What kind of system is this? Is this a determinate system or indeterminate system?
Indeterminate.
Indeterminate system, and it has an indeterminacy of 2, correct? Static indeterminacy of 2, because axial deformations we are ignoring. Okay, so for such kind of a system, what method do we know and how to solve an indeterminate system? Because we cannot use the stiffness method yet, because that's what we are developing.
Flexibility.
Flexibility method, right? Very good. So in order to solve this, what do we have to do? We have to reduce this into what? This is an indeterminate system. We have to reduce it to a determinate system.
Determinate system.
Very good. So what we will do is we will reduce it to a determinate system, and this is a very good determinate system that is very easy to solve, correct? A cantilever wherein we have released the degrees of freedom here. Okay, and what we do is we apply an unknown F and we apply an unknown M. Okay, and for this the question here is actually I started with the formulation of F1, sorry, so I should have picked the different ones. 1 second. Okay, so retracting a little bit. Let me retract a little bit. Let me erase this diagram. What I want to do is, this was my fixed beam, and I want to calculate the forces for this delta beam equal to 1. Okay, so I want to know F1 3, F2 3, similarly F3 3 and F4 3. This is what I want to calculate. Okay, because this delta is actually corresponding to third degree of freedom. Okay, so we release that degree of freedom and we apply an F and M, because these are unknown forces. This is what the flexibility method is all about. And the trick is that this combination of F and M should be such that I get a delta of 1 and I don't get any other displacement anywhere. Okay, and that should be possible, right? So let's do that. So what do we need to do? We need to calculate delta at this location and theta at this location. Likewise, we calculate delta at this location and theta at this location. We will call these delta and theta because of F, and we will call this delta and theta because of M. And what do we need to make sure is compatibility. So should make sure that delta F plus delta M is equal to how much?
0.
0?
1, sir.
Yes, you want to produce a unit deformation there, right? And theta F plus theta M is equal to how much?
0.
0.
0, because we don't want to produce any slope here. Sorry, is equal to 0. Okay, so first we have to calculate delta F, delta M, theta F, theta M. Okay, so this is the beam. My bending moment diagram for this problem will be, if I can plot the bending moment diagram, maybe I'll draw it here. I apply a force F here, like here. So what will be the bending moment diagram? Anybody? How will be the bending moment diagram for F force?
Linearly varying, so
Linearly varying, right? So maximum moment will be
F into L.
F into L. Okay, and I'm calling it positive because bottom side is in tension. Okay, and for the other case, okay, so let me solve this one first. So theta at this location, which method would I use to calculate theta here? It's a cantilever problem.
Moment area method.
Moment area method, right? So FL divided by EI. What is the area of this triangle? This is the area of this triangle, right? FL divided by EI, of course. So I have divided by EI multiplied by L by 2. That is the area. And delta here would be this area. So that is FL square by 2 EI. Area multiplied by what? The centroid distance from the location we are calculating the displacement at. That is 2L by 3. That will be FL cube by 3 EI. Agreed? Everybody is on board with this? FL cube by 3 EI. That is my delta because of F. Similarly, the bending moment diagram because of an applied M will be how much? Uniform M. Correct? So theta will be M divided by ML divided by EI, and delta will be, these are because of M, delta will be ML divided by EI multiplied by L by 2. Correct? This is where the centroid is. Okay. Fine. So now all I have to do is I have to apply the compatibility conditions. So the first one is theta F plus theta M is equal to 0. So theta F is FL square divided by 2 EI plus ML divided by EI equals to 0. So from here I can get M equals to minus EI, and EI will cancel out. L square will cancel out. Is minus FL by 2. Am I right? Okay. That I can substitute into the other equation. The other equation is delta F plus delta M. So this one was theta F plus theta M equals to 0. Then we will do delta F plus delta M equals to 1. So delta F is equal to FL cube divided by 3 EI plus delta M is equal to M L square by 2 EI. Okay, so M will be substituted with minus F L by 2 multiplied by L square by 2 EI and equals to 1. Fine. So this is basically FL cube by 3 EI minus FL cube by 4 EI. What does that mean? 1 by 3 minus 1 by 4. 1 divided by 3 minus 1 divided by 4 is how much?
1 by 12.
1 by 12.
1 by 12. So FL cube divided by 12 EI is equal to 1, which means F equals to 12 EI by L cube. Okay. And if you notice, this F was applied in the direction of third degree of freedom. Correct? That's where it was applied. So basically, this term is nothing but your F33 term. Okay. Similarly, we can calculate M. M will be basically your m was equal to minus fl by 2, right? So minus f is 12 ei by l cube multiplied by l by 2. So that is 6 ei by l square. Is that correct? So m is nothing but your f43. You agree? It is in the fourth degree of freedom. So therefore f4 because of unit displacement in third. So f43, and that is minus 6 ei divided by l square. Okay. So these are the displacements because of, these are the forces because of unit displacement in third degree of freedom. Now all I have to do is f33, f43 are calculated. We can now use equilibrium to calculate f1 and f2 also. This was my beam. We have solved the system now. Some internal forces have been calculated or some reaction forces have been calculated. F33 was this force acting is 12 ei divided by l cube, and F43 is basically this force, right? Clockwise now, 6 ei divided by l square. Now it has to be balanced. So of course the force balance will require that on this side we apply, this is Newton's first law again, 12 ei by l cube. Okay, and then if you see the moment balance, you will see that the moments are not balanced right now. It is 12 ei. If I take the moment about this point, it is 12 ei divided by l cube multiplied by l, that is in the counterclockwise direction, minus 6 ei divided by l square. Okay, so what is the net balance? 6 ei divided by l square. So right now I have total unbalanced moment of anti-clockwise 6 ei by l square. So I have to apply a clockwise moment of 6 ei by l square to balance it. So this will be supplied by the boundary condition on this end, on degree of freedom 2. Fine. So as a result, my F12 can be written as minus 12 ei divided by l cube, and F12 nahi, this should be F13, and F23 can be written as, this is again clockwise, so minus 6 ei divided by l square. Does that look good? Yeah. These are the expressions. F13 is minus 12 ei by l cube. F23 is minus 6 ei by l square. F33 is 12 ei by l cube. And F43 is minus 6 ei by l square. Okay. So likewise, you will get forces at all 4 degrees of freedom for creating a unit displacement in the third degree of freedom. Likewise, you can do it for all other cases. We will do one more for unit displacement at the fourth degree of freedom. Okay. So we want to calculate the stiffness terms for delta 4. So this time, this is the beam, and we want to apply a unit displacement in the counterclockwise direction. That means the beam deforms this way. Okay. And it has rotated like so. And this theta is equal to, which you can call also delta 4, is equal to 1. Okay. And we want to make sure that only delta 4 is non-zero. All other deltas are 0. Delta 1, delta 2, delta 3 are all 0. Okay. Now, from before, what does not change is the definition, the calculation of theta f, theta m, delta m. Okay. So let me quickly select. Similarly, let me select this also. Okay, this we had derived already. What changes this time is the compatibility equations. The new compatibility equations should be theta due to f plus delta due to f is equal to how much? Sorry, what am I saying? Theta due to f plus theta due to m is how much?
1.
1. And delta due to f plus delta due to m is equal to 0. Because there is no delta produced here, only theta is produced here. We do that. So theta f plus theta m. So let me first solve this one. Delta f plus delta m. So delta f plus delta m f l cube divided by 3ei plus ml square divided by 2ei equals to 0. So my m will be equal to, this ei will cancel out, m will be equal to minus fl by 3, 2 by 3 fl. Is that correct? Is that correct? Now, coming back to this one, theta f plus theta m. This is basically theta f is equal to fl square by 2ei plus ml by ei is equal to 1. Substituting the value of m, I get fl square by 2ei minus 2 by 3 fl square by ei is equal to 1. Right? So 1 by 2 minus 1 by 3 is how much? Sorry, 1 by 2 minus 2 by 3. Right? Did I make a mistake here somewhere? Minus 1 by 6, right? 2 by 3 minus 1 by 2 is 1 by 6, right?
Yes, sir. Minus 1 by 6.
1. So F is equal to 6ei minus 6ei divided by L square. Okay. And this F corresponds to force in the third degree of freedom for a unit displacement in the fourth degree of freedom is equal to minus 6ei divided by L square. Okay. The moment will be equal to now minus 2 by 3 multiplied by, that will become plus now 6ei by L square into L. That is 4ei by L. So my F44 will be 4ei by L. Now I need to solve for the other two unknown forces. I got, it's downward force actually, 6ei by L square, and I got counterclockwise force, counterclockwise moment of 4ei by L. I need to find the forces here. Okay. So of course the force balance will require that I have to have a 6ei by L square force in this direction. Okay, there's no escaping from that. That force will of course be there. In addition to that, I also need to do the moment balance. Okay, so we have done this exercise before. The moment balance will require, let me take the moment about this point. So I got 6ei by L square multiplied by L. This is in the clockwise direction, minus 4ei by L. Okay, this is in the counterclockwise direction. The total moment is 6 minus 2 is equal to 2ei by L. So I have got a net moment acting in the clockwise direction that is equal to 2ei by L. So I have to apply a balancing moment, otherwise the system will not be in equilibrium. I need to apply a balancing moment of 2ei by L in the counterclockwise direction. Agreed? Agree, right? So this will be the moment demand, moment requirement at this end. Otherwise the system will not be in equilibrium. So my F14 turns out to be this value, right? This value, 6 EI by L square. This is upward direction, 6 EI by L square. And F24 turns out to be, it is in counterclockwise direction. So 2 EI divided by L. Divided by L. So it is 6 EI by L square, 2 EI divided by L minus 6 EI by L square, 4 EI by L.
Sir, 2E by L should be in clockwise.
See, the thing is that if I'm taking moment about this point, 6 EI by L square is in clockwise direction. 4 EI by L here is producing an anti-clockwise direction. And 6 EI by L square is bigger than the effect of 6 EI by L square multiplied by L. That is this moment. That is bigger than this moment. So that means the net of these two is in the clockwise direction. So in order to balance it, I have to apply a moment in the anti-clockwise. Yeah, I was saying anti-clockwise direction, but I was drawing it in the clockwise direction. Yeah, so sorry. So 2 EI by L has to be acting in the anti-clockwise direction. That's why it is positive. Yeah, now it is clear?
Yes, sir.
Yeah. Sorry, I drew it wrongly. Okay. So this is 2 EI by L minus 6 EI by L square and 4 EI by L. Okay. So likewise, you can develop the terms of the stiffness matrix. So these are the terms corresponding to unit displacement in the fourth degree of freedom, and these are the terms corresponding to a unit displacement in the third degree of freedom. And the overall stiffness matrix, likewise, you can develop the terms for force terms for the unit displacements in the first and second degrees of freedom. What you see here, these are the displacements in first degree of freedom, and because of that, some forces will develop. Likewise, for the second degree of freedom, and from there, essentially, we develop the stiffness matrix. What it means is that if this is your beam, this is my beam, and 1 and 2 and 3 and 4 are the 4 degrees of freedom. For a unit displacement in 1, I can get all 4 forces, F1, F2, F3, F4, by putting this kind of a stiffness matrix, wherein these are the terms corresponding to delta 1 is equal to, which are the terms for delta 1 is equal to, all these terms are corresponding to delta 1 is equal to 1. Okay, so if you multiply this with delta 1, you will get F1. If you multiply this with delta 1, this with delta 1, you will get F2. You multiply this with delta 1, you get F3, and you multiply this with delta 1, you will get F4. Fine. For F3, like we had derived before, for the delta 3 that we had derived before, you got this vector of the stiffness matrix. Okay. So these are the 4 forces, F1, F2, F3, F4, for delta 3 equals to 1, and all other deltas being 0. Okay. So this is what is called stiffness matrix. Now, if you look closely at this stiffness matrix, the terms of this stiffness matrix are symmetric, right? So you got 6 EI by L square here, you got 6 EI by L square here. So diagonally opposite terms are equal. Minus 12 EI by L cube, minus 12 EI by L cube, minus 6 EI by L square, 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 2 EI by L, 2 EI by L, 6 EI by L square, 6 EI by L square. Okay. Another thing that you should notice here is the 2 EI by L and 4 EI by L relationship. So for a unit rotation, in order to produce a unit rotation at one point, at that end, you have to apply 4 EI by L. But at the opposite end, you have to apply only 2 EI by L moment. Right? You remember this concept in the moment redistribution method or moment distribution method? Correct? So when you were releasing a moment at one end, the amount of releasing the rotation, you have to apply a moment of 4 EI by L, but the other end you are applying a moment of 2 EI by L, right? That is these terms. Okay. So force required for, let's say, for in order to get a unit value of delta 2, the force required at second degree of freedom at the same location is 4 EI by L, but the force required at the fourth degree of freedom here is only half of that. Any questions from this so far? Okay, so now that stiffness matrix basically represents your relationship between the 4 forces and the 4 displacements. These 4 forces correspond to the 4 degrees of freedom, 1, 2, 3, and 4, and 4 displacements at the same degrees of freedom. And basically, this essentially means is that there are 4 different 4 algebraic equations. F1 is equal to this much of delta 1 plus this much of delta 2 plus this much of delta 3 plus this much of delta 4. Okay, and so on. So basically, out of these 4 equations, how many values can we solve for? So how many unknowns can we solve using these 4 equations? These are 4 algebraic equations. These can be used to solve only 4 unknowns, right? So these are all known values, whatever is there inside the matrix. What could be unknowns are F1, F2, F3, F4, and delta 1, delta 2, delta 3, delta 4. Out of these 8 unknowns or potential unknowns, at least 4 have to be known to us. Then the remaining 4 can be solved for. You get me? Okay. So let's say one F1 is known and the 3 deltas are known. Then we can solve for the remaining 3 Fs and 1 delta. Okay. Is that okay with everybody? Because these are 4 equations, we can solve only for 4 unknowns. Okay. So what we will do is today we will also spend some time in discussing how is this method applied. So there is something called assembly of stiffness matrices. That's where we will focus today. So, and we will do through an example rather than talking in abstract. So let's say this is a plane beam system. Okay, it's a problem. It's a beam, plane beam, but it has an intermediate support in the middle, and then there is a load acting here. So using it, and if you look closely, you will find that this is a determinate system. Okay. So a determinate system, as I mentioned, can also be solved using the stiffness method of analysis. You can solve it directly using your simple force equilibrium equations, but we will try to use the stiffness method. So for the stiffness method of analysis, it would be an obvious choice to break this member into 2 parts, right? One part here and the other part here. Okay. Because you have an intermediate support and you don't have the formulation available for a beam which has an intermediate force acting. Our formulations are available only for the beams which don't have any intermediate forces acting on them. Okay, so we will have to split this into 2 parts. Fine, or an intermediate known force available. So what we do is we break this into 2 members. Member 1 marked here, member 2 marked here. Okay, both members are 2 meter length. And the force 5 kilonewton is acting here. This force is unknown. Third. And then we define the degrees of freedom or the kinematic indeterminacies. The overall kinematic indeterminacies are 1, 2, 3, 4, 5, 6. Okay. Overall degrees of freedom are 6 degrees of freedom are there. If you notice, you will see that 3 and 4 degrees of freedom are common in member 1 and member 2. They are present in both. However, 1 and 2 are present only in member 1, and 5 and 6 are present only in member 2. Fine. Then, just like we have derived the expressions for the stiffness method, stiffness matrix, we can develop the stiffness matrix for member 1. So a stiffness matrix for member 1 is basically this one, which has terms of 12 EI by L cube, which are displacement terms, displacement force terms, then these are displacement rotation terms, and so on. And these are rotation terms, rotation momentums for EI by L, or TI, 2 EI by L. Okay. So we write the stiffness matrix for member 1, which is for each row and each column are marked for the corresponding degrees of freedom they belong to. So this is 1, 2, 3, 4, 1, 2, 3, 4. Okay. This term is 1, 1 term, 1, 2 term, and so on. Likewise, we write the stiffness matrix for member 2. This is member 2, and the stiffness matrix is basically the same because EI is same and length is same. So 2 meters is 2 meters. Anyway, that is not incorporated yet. So since it's a plane beam, you got the same stiffness matrix. Only thing that changed was that these individual columns and individual rows now belong to these degrees of freedom: 3, 4, 5, 6, 3, 4, 5, 6. Okay. Earlier they were belonging to 1, 2, 3, 4, 1, 2, 3, 4. Any questions so far? Now we will simply substitute the value of L. So EI is not given. We will keep EI as constant, and we can take EI out because all the terms have that EI value. So we will take EI out. We are left with 12 by L cube, 6 by L square, and so on. So that 12 by L cube when we substitute the value of L, we get that value as 1.5, and all those values are calculated and written here, and EI is taken out. So this is the stiffness matrix for first member. This is the stiffness matrix of the second member, this one. Again, the values of L are substituted in the stiffness matrix. Okay. Now comes the question of developing the entire stiffness matrix, because what is happening is that, let's say I apply a unit displacement at the third degree of freedom. Okay, so if it was only one member, I would have gotten some resistance at 3. Okay, and that resistance would have been delta 33, that is 1.5 EI, this term. Okay, but this is not just this member. I also have this member where the 33 term is here, which basically means that if I push this joint, this location by 1, while it is still a part of both members, I should get 1.5 EI resistance because of this member, and I should get 1.5 EI resistance from this member, which basically means I should be able to add this 1.5 here with this 1.5 here, because they both correspond to the degree of freedom or the coefficient 33, F33. Okay, if you are not sure, this is 33, right? This is 3, this is 3. So this is F33, and this is 3 here, and this is 3 here, F33. Okay, so which basically means that I need to assemble the global stiffness matrix. So this is the, let's say this blue colored one is the stiffness matrix for member 1. The pink one is the stiffness matrix for member 2. If I want to write the global stiffness matrix, it will have 6 degrees of freedom, 1, 2, 3, 4, 5, 6, correct? Like the structure has 1, 2, 3, 4, 5, 6. However, when we put the individual member stiffness matrices, you will see this will occupy, the blue one will occupy this much of space, 1, 2, 3, 4, 1, 2, 3, 4. The pink one will occupy the space corresponding to 3, 4, 5, 6, 3, 4, 5, 6. Okay, and there will be an overlap of 3, 4, 3, 4 here. And there will not be any terms introduced at 5, 6, 1, 2. Likewise, 1, 2, 5, 6 here. So these blocks will be zeros, and these blocks will be having an overlap. Overlap basically means you can simply add the terms that are overlapping. Okay, so our member 1 stiffness matrix was this one. Member 2 stiffness matrix was this one. We add the 2. What we get is, which terms are going to overlap? This ones. This one is going to overlap with this one. So 1.5 is going to turn into what value?
3.
3, sir.
3. And this term is common, is occupying the common space, 1.5 and minus 1.5. So this term will turn into
0.
0. Likewise, this term and this term will turn into 0 when they are added. And this is 2 and this is 2, so that will become 4. We are simply arithmetically adding them. So that's what happens. This becomes 3, these are 0, 0, and this is 4. The rest of the stiffness matrix for member 1 is same. Likewise, the stiffness matrix, the rest of the stiffness matrix for the member 2 is also unchanged. And these have 0 terms here on this side. Okay. Now we need to explain and physically understand what these values and what these values and what these values mean. The rest of it is pretty straightforward. It is taken directly from the earlier stiffness matrix. So can somebody tell me what do these 0 values mean for the entire structure? Anybody?
So when the displacement is applied at 5, there is no influence on one force.
That is correct, but does that sound okay? If I have a structure like this here, I apply a unit displacement at 5, should I not have any force at 1? Anybody? So the answer was that if these terms are 0 and this term corresponds to the degree of freedom the relationship between degrees of freedom 1 and 5, right? So if I apply, or this term, basically they are, since it's a symmetric matrix, this is 0 and that is also 0. So if I apply unit displacement at 5, you should not have any force required at 1, or any additional reaction force at 1. Similarly, if I apply a unit displacement at 1, I should not have any force at 5. Okay, so are these both true? Does that seem okay? Especially this one, if I apply unit displacement at 5, should I not have any additional force at 1? What am I missing here? That's what this stiffness matrix definitely means, that if I apply unit displacement at 5, there will be a force at 5, there will be a force at 3 onwards. So 3, 4, and sorry, if I apply unit force at 1, unit displacement at 1, or let me talk about this column. So let me talk about this column. So if I apply unit displacement at 5, my force at 1 will be 0, my force at 2 will be 0. But forces at 3, 4, 5, 6 will be non-zero. So I'll have some force demands here, 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 if I apply unit displacement here, but not here and here. Nobody can answer that. Why are these terms 0, F1 and F2? These terms F1 and F2, why are they 0? Okay, I'm not going to move forward until you answer that.
Excuse me, sir.
Yeah.
Sir, I think in the first place, we already divided the beam into 2 parts. That's why it's 0.
We did not divide it into 2 parts. Now we have assembled them back. I think you are on the right track, but it's not quite answering the question. Like, it's not a good enough explanation. We did not exactly divide it. We developed the stiffness matrices independently. We did not literally divide it, actually. We did something slightly different. Okay. I take back my word. I'll move forward. So the deal is, this is the beam, right? Correct? This is the problem given to you. But this stiffness matrix does not actually belong to this beam. This stiffness matrix belongs to the beam that is this one. Okay, 1, 2, 3, 4, 5, 6. Now it's obvious, right? So when I'm saying I'm applying a unit displacement at 5, what am I doing actually? I'm saying I'm applying this displacement like this. Okay. So when I do that, I will have to apply some force here. I have to apply some force here. I have to apply some force here. I have to apply some force here. But once we make sure that the displacements here are 0, it will not translate into any forces at 1 and 2. Agreed? When I'm applying delta 5, I'm making sure that I'm not applying any other deltas. That is what the stiffness matrix means. So this entire column here corresponds to delta 5. And any term here ensures that no other deltas are present. If I'm talking about only this one. Is that clear? Does that make sense now?
Yes, sir.
So if we maintain these restraint at 3 and 4 location, then of course there is no additional force required at 1 and 2. No matter what I do at 5 or 6 for that matter. Similarly here, I have restrained it here. I have restrained it here. And here, instead of restraining it, I allow it to rotate. I'm going clockwise. I allow it to rotate in a counterclockwise direction. Delta 6 is equal to 1. But whatever forces were required, they were all satisfied between 3, 4, 5, 6. So you don't have to apply any additional force at 1 and 2 because it is already fixed here. So no effect of this one is transmitting beyond this boundary condition. All that is absorbed, all that effect of delta 6 or delta 5 are absorbed at 3 and 4. Okay, so that's why you have these terms as 0. What does that term 3 mean and what does that term 4 mean? It means if I apply, so if it was a single beam, I were to apply a unit displacement here, I would have required 1.5 EI force. But now this is, both beams are acting and they are acting in parallel. So if I want to apply unit displacement here, I will have to pull it by 3 times the EI. That is double the value of the original. Originally it was 1.5 EI. That means both beams have to deflect by that amount. Similarly, rotation. So if I want to produce a unit rotation at 4th degree of freedom, so I want to, let's say, if I want to make it deform this way. Okay, sorry, you're poorly drawn. Like this. If I want to make it deform this way, this beam has to rotate and this beam has to rotate. That's why instead of a 2 EI, I have a term of 4 EI. Fine. The rest of all are still the same as before. Okay, so this is my stiffness matrix now, which corresponds to the 6 displacements and the 6 forces, F1 to F6, delta 1 to delta 6. Is that fine with everybody? Now, we have got 6 equations here, and we have to see how many unknowns we got. If you look again, we have got delta 1, delta 2, delta 3, delta 4, delta 5, delta 6, and the 6 forces. 6 displacements, 6 forces. Total, we have total 12 potential unknowns. Out of which, how many are actually known to us? Delta 1 is known, correct? Delta 3 is known. So delta 1 is known. How much is delta 1? 0.
0, sir.
Delta 3 is known, that is also 0. Okay, delta 2 we don't know. There will be actual rotation, we don't know that how much it will be. There may be actual rotation at 4, we don't know. Delta 5, delta 6 are not known. Okay. Do we know force in one direction? How much reaction are we getting? Don't know yet. Do we know how much moment are we applying at this joint?
0, sir.
0.
Yes. Similarly, F3 we don't know, but we know F4 is 0. We are not applying any net moment here. Okay. F4 is 0. And F5 we know already. It is 5 kilonewton in downward direction. So this is minus 5. And F6 is 0. So how many do we know? 1, 2, 3, 4, 5, 6. Total V6, 6 known and 6 unknowns. Now we can deal with these equations. Okay, so out of 12, we have 6 values are known to us and 6 are unknown. So we can solve this. How do we do? We first substitute the values wherever we know them. So we have substituted these 0 values. We have substituted these 0 values and minus 5 value. Now what happens is that the locations where displacements are 0, we call them restrained degrees of freedom. So which degrees of freedom are restrained? These are restraint degrees of freedom. And where we know the force values, what do we call them? Free degrees of freedom. We don't know the displacements there. So we don't know the displacement at 2, but we know the force value at 2. So we will call it 2, 4, 5, 6. These are free degrees of freedom. So in the next step, what we need to do is we need to segregate in this matrix, segregate the degrees of freedom which are restrained versus free. Okay. So initially they are all mixed up, right? This is restrained. This is restrained. And the terms corresponding to these two in the stiffness matrix are the first column. This entire column multiplies with this 0 or this term. And this third column, that one multiplies with this term always, right? So F1 is equal to 1.5 delta 1 plus 1.5 delta 2 minus 1.5 delta 3. So this one always multiplies with this term, and this one always multiplies with this term. Okay. Likewise, if we see this one, this one, this one, this one, these are rows, rows of second degree. Likewise, fourth one. And likewise, actually fourth, fifth, sixth, they are all the same. They are both coming under the free degree of freedom. So what we will do is we will move the terms of restrained degree of freedom on one side and free degrees of freedom on one side. So F1, F3 are restrained degrees of freedom. We will move them down like so. Okay. We will move them down. So when we move F1 and F3 term down, we also move the corresponding coefficient terms in the matrix, but we don't have to make any change in the displacement matrix because we are not doing any column operations here. Okay, we are only doing row operations. So row operations are done between this matrix, this vector and this matrix. Fine. So the first column has been moved to this location. The second column has been moved to this location. Rows, I meant row, sorry. The first row is moved to this location. The second row is moved to this location. So then subsequently, let's do the column operations also. So the column operations are in such a way so that all our known deltas are on one side and unknown deltas are on the other side. So this is one known delta, and this is the other known delta, which are marked in red and green here. So we will try to move them to one side. We will move them to the bottom. What we do is this 1.5 comes here. This particular column comes here, and this entire column comes here. And correspondingly, this 0 value comes here, and this 0 value comes here. Okay. Now, basically, what we have done is there were these 6 algebraic equations. F1 is equal to something something delta 1 plus something something delta 2 plus something something delta 3. Okay. All we have done is that we have reshuffled the equations a little bit, moved some of these equations up and moved some of these equations down, and we have put some of these terms before and some of these terms after. All that we have done in this entire process by moving the rows and columns like so. Okay. So we have not changed anything in the fundamental level in the equations. Okay. By the way, I'm out of time now. So with that, I get this equation, and this equation now has this beautiful thing where I have all the known forces first, then unknown forces, and I have all the unknown displacement first, and then the known displacements. Okay, and the corresponding stiffness terms. In the next class, we will continue from there. Okay, let me stop immediately.